Alright, so now we're actually going to start learning how to calculate the test statistic and the p-value. So we've actually done this before. We've learned about this in the previous chapters, so now we're just going to do it in the context of hypothesis testing to help us make decisions about the statements we're making about the population parameters. So there's 3 different scenarios, but for the first one we're going to do a one-sample z-test. There's a difference between a one and a two-tailed test. So basically what those are is they basically affect the probabilities that you calculated. So it's a little confusing to kind of understand. So we're just going to actually go through an example, and then I'll give you an example for the one and the two-tailed test, and then just by doing it, it will make more sense. So don't worry about the one and two-tailed test for now. So in this first situation, we have basically one sample, and we're using the z-test. So remember, a z-test, a z statistic, is when we know the true population standard deviation. So that's when we use the z-test. So that's the first scenario that we're going to do. So we're going to have a mean, a population mean that we're interested in. We know the population standard deviation, so we're going to use the z-test. And the other two cases, we have we're looking at the mean, but we don't know the population standard deviation. So we have to estimate this from the sample. That's when we use a t statistic. Remember that from previous chapters. And then the last one is we're going to use a z statistic as well, but that is when we're going to use look at population proportions instead of mean. So those are the 3 scenarios, but for the first one, like I said, we're doing the one sample z-test. We know the population standard deviation. So here's our example. Hilltop Coffee states that a can of coffee contains 3 pounds of coffee. The FTC tests this claim to make sure consumers are protected. That is, coffee cans are not being underfilled. So of course, like I said in a previous video, not all cans contain exactly 3 pounds of coffee, but as long as the population mean is at least 3 pounds per can, right, on average, Hilltop is safe in making this claim. So we want to test this claim that the population mean is at least 3 pounds, because right, if they're overfilling it, that's okay. Consumers are still protected. So this is what this note means. The company is safe so long as there are at least 3 pounds of coffee. That's probably not ideal though for the company, because if the mean is higher, they're basically giving away free coffee. But the FTC doesn't care about that. They just want to make sure consumers are not getting less than what they are promised by the statement given on the can. So right, let's go back to understanding our steps. We have 4 of them. The first one is to state our hypotheses. So in this one, this is the case where we have an assumption that we're challenging, right? This is the case where we're looking at production or manufacturing processes. So we begin by assuming the statement is true. The statement on the can is that there's 3 pounds of coffee. So right, remember, we don't care if it's more than 3 pounds. We want to make sure it's just at least 3 pounds. So that's our null hypothesis, that mu, the population mean, is at least 3 pounds. The alternative is the opposite, that mu is less than 3 pounds. In this situation, we hope the company is correctly filling the cans. So we hope, right, to fail to reject the null. We'd like to find support for the null, that they're properly filling the cans. So let's test this. So right, step 2, determine the level of significance. Let's just go with thinking about this, but remember, alpha of 0.05 is the default. So in research, we often report the p-value and say we found support and or the results are statistically significant. Sometimes we leave out statistically and we just say the results are significant. We mean they're statistically significant after analyses. This is important because we're not saying they're significant as in they're important. We're saying that they're meaningfully that the results are meaningful, meaning that we did analyses to find statistical support. So, it's funny because I've done stats for so long I overlooked this, but the word significant doesn't mean that they're like important. It just means that they're statistically significant. So, meaning that we found results that are less than the given p-value. So if p, right, is less than 0.05, we have significant results. If they are less than 0.10 but greater than or equal to 0.05, we say the results are marginally significant. That's just some terminology you might see in the field. However, even though, like, so in the research I do, that we don't upfront state alpha. We just have a default of 0.05, and we just report our exact p-value. But with proper research and studies, and especially with something like this study that we're looking at right now, with production processes, you should define alpha before you collect your data and do your study. So, so Kristen, what should we do? How should we set it? 0.01, 0.05, 0.10. So this is actually a decision you have to make, and you have to make it based off of the confidence in your results. So if you need better confidence in the decision that you're making, and you don't want to falsely make a type 1 error, you want to make alpha smaller. So let's take a step back. What is a type 1 error? That this seems like a bad thing, right? It's got error in it. We don't want to do that. What does that mean? A type 1 error is when we reject the null when we shouldn't have. So in this case, the null is actually true, but we reject that. So in this example, think of how bad that would be, right? Because the null says that we're properly filling the can. So we would be telling the company, right, if we found significant results, we would be telling the company that they're not properly filling the cans and they're in violation. So if you're in violation, usually you get a fine, you have to change your production processes, right? So we wouldn't want to falsely accuse this company of that. So we want to be really conservative. We want to make sure that we're increasing the likelihood that we are more confident in the results that we're making. So we want to make alpha smaller. So we're going to set it as 0.01. So let me just reiterate that. Remember, the smaller your p-value that you get, right, that's basically saying that if your null were true, the probability of getting your results are this p. So the smaller your p-value gets, the more evidence you have to reject your null hypothesis. So it's basically a way of looking at the confidence in the decision that you're making. So we want to be pretty confident because, like I said, this is a pretty big, important decision that we're making. Not as though, you know, some research decisions aren't or whatever, but in terms of, you know, falsely accusing a company of not properly filling their cans, we don't want to do that. So let's set our alpha as 0.01. So here's the data, right, for step 3. Sorry, that's repetitive. You have to analyze your data. So in analyzing our data, we're going to calculate two things, the test statistic and the p-value. So technically, both of them will provide us with enough information to make a decision in terms of rejecting the null or failing to reject the null. But the p-value gives us more information. But we're going to calculate both of them because we actually need the test statistic z in this case to calculate the p-value. So let's assume we had a sample size n of 36, the sample mean is 2.92, and the population mean is known to be 0.18. So if we look at it, right, 2.92 is actually less than 3, but remember we have to determine if this is statistically significant, right? We have to go through the whole process, right, because objectively you might look at that and be like, yep, it's less, but remember, right, there's room for error, so we need to go through the statistical process of analyzing these numbers. Right, we're taking the subjectivity out of it and trying to be as objective as possible. So remember, we've already learned how to do this in previous chapters, right? We have to calculate our test statistics so that we can calculate our p-value. So we've already done this in the past, right? To calculate a test statistic, right, in this case z, we just find the difference between our population value and our sample value, and then divide that by the standard deviation, right? That'll give us our z-score, which we can use to calculate p, right? So the standard deviation that we divide by, right? Remember, it's the standard deviation of the sampling distribution, right? And the standard deviation of the standard deviation of the sampling distribution is known as the standard error, right? We've already learned about that. So to calculate the standard error, it's just the standard deviation of the population divided by the square root of n, right? We've already learned how to do this in previous chapters. So let's just plug in our values. 0.18 divided by the square root of n is 0.03. So this is our standard error, right? The standard deviation of the sampling distribution. So let's continue to plug values in. So to get this test statistic, our z value, right, just find the difference between our sample mean, right, our point estimate, which is 2.92, minus the mean, which is 3 of the population, and divided by that standard error is 0.03, we get negative 2.67. So that's our test statistic. So it's just by looking at it, we can actually tell if this is significant. We'll get back to that in a second. If you remember this figure that I showed you in a previous chapter, it tells us what our confidence level and our alpha is and what the z-value is. So remember, we used 0.01. So the z-score is 2.57, so it's actually pretty close. But this is a two-tailed test. We're actually using a one-tailed test. So remember, I told you that that's something to consider. So I'm not going to actually talk about this just yet. Let's just realize we calculate our test statistic, and we can use this now to calculate our p-value, right? And if our p-value is less than 0.01, we can reject the null or fail to reject the null. So let's do this. So we have to determine what our critical value is. So our critical value is the a test statistic value that we can compare to the test statistic that we just calculated to determine if we can reject our null or not. So again, this is something that we've already done in previous chapters, right, where we can, if we know the probability, we can calculate the z-score that's associated with it. So we've already learned how to do that in Excel. That's just equal to equals norm.s.inverse, where we have one argument in this function, which is a p-value. So our p-value, right, is 0.01. So that will give us a test statistic value of, or a z-value of negative 2.33. So this is the critical value. This is what we're comparing our test statistic to see if we should reject the null or not. So we have negative 2.33, I'm rounding, and the test statistic we just calculated is negative 2.67. So this value is actually larger than our critical value. So in this case, remember, larger test statistics mean we have more evidence to support rejecting our null. So because this test statistic that we calculated is larger than the critical value, right, we can reject the null. Right, so let's just take a step back and say that one more time, right? So we went through the process to calculate our test statistic, and we have to compare this to another, what's called critical value, to determine if we should reject the null or not. So how do we calculate our critical value, right? We have to know what our p-value is to calculate our z-score, which is going to be our critical value, which is negative 2.33. So we can compare that to our test statistic to determine if we should reject the null or not. If our test statistic, right, is right, if we compare that to our critical value, right, we can determine to reject the null or not. So our value, I think I may have said that, I'm just going slow because I think when I talk so fast, I think I may have said it wrong last time, so I just want to make this clear, right? Our value is smaller here. It's less than negative 2.33, so we'd reject the null. I think I said last time that the larger our value is, we reject it. It's the absolute value. I think that's where I may have confused, if I confused you, because you're probably looking at this with the negative values. I just automatically take the absolute value. This is the problem with teaching stats sometimes, is that you do it so often that it just comes to you, but when you teach it, you have to slow down a little bit. So when we're looking at test statistic, right, the larger its absolute value, the more evidence you have to reject the null. So that's the correct way of saying that. So if we just took the absolute value of this, right, 2.67, right, the larger this value is, the more evidence we have to reject the null. What's large, right, with z-scores, right, any time you get a value around 2, right, for, right, somewhere around 2 for a confidence of 0.05, right, that's the critical value, somewhere around there. If you have 0.01, it's 2.58. So we know we're right around that region. Of course, this is depending on a one or two tailed test, like I said before, but just to give you an idea of what values you're looking at, that will give you a good idea. So in terms of us making our decision, right, we have negative 2.33 compared to negative 2.67, right? This value is less than our critical value, so we reject the null. So in this case, if we're rejecting the null, remember our null says that they're properly filling the cans. So if we're rejecting that, that means that this company is underfilling their coffee cans. So they're in violation. So this is not good. So with this approach, we can only reject or fail to reject the null. In this case, we're rejecting it. But the thing is it doesn't really tell us how significant the results are. They're just saying that, hey, we're just rejecting the null. So this, what I just showed you right here, this is actually, there's another learning objective about the critical value approach. This is the critical value approach, where you take your test statistic and you compare it to a critical value to determine whether to reject the null or fail to reject the null. Right? You will come to the same conclusion as with the p-value approach, except with this approach right here, the critical value approach, you don't have as much information. So let's actually continue and do the p-value approach to see that you come to the same conclusion. So remember, our p, right, our alpha was 0.01. So if our p is less than 0.01, we're going to reject the null. So our p-value is 0.003. I'm going to show you that in a second. Right? It is less than 0.01, so we do reject the null. So we are coming to the same conclusion, but now see how we're getting more information? We're getting a specific number, right? We're not just coming to a conclusion, but we actually have a specific number in terms of the p-value. Now, of course, you might argue that, well, we also have a number here too, so you are getting the information, but typically the p-value is a little bit easier for people to interpret because these values, right, they change, right, depending sometimes on this test statistic that you have, whether it's one or two tailed tests. The p-value is a little bit more intuitive, so that's why sometimes people prefer the p-value approach. So that's what all this information kind of is telling us. So let's actually determine how we calculate the p-value. So again, it's just in Excel, right? So we know that if we can use the equals norm.s distribution, because this is a normal distribution, it's the standard normal that we're using. This function takes two arguments, right? The cumulative function, the cumulative argument here is true. And then we plug in our test statistic, which we calculated to be negative 2.67. So if we do that, it calculates our p-value for us. So with rounding, that actually should have been 0.004, but you get the idea. So let me just show you in Excel, right? I mean, I have them there written for you. But again, in case you forgot, again, this is just, if this isn't clear, go back to the old videos that we've looked at from previous chapters. So again, in terms of calculating our critical value, so right, what is the critical value again, Kristen? I forgot. That's okay. Right, with our first approach, we have our test statistic that we calculated, right? And we need to compare that to a critical value to determine whether to reject the null or not. So to calculate the critical value, that's where we go to Excel and type in norm.s.inverse. We plug in our probability, and it will give us our critical value that we compare it to, right? Because ours is smaller than this value, right, we reject the null. Right, because it's, when you think about your probability distribution, right, this is basically to the left, right, it's on the left side of the symmetrical distribution, it's in that tail, so it's beyond this critical region, so we would reject the null. And then going to this example, okay, how do we calculate the p-value? So again, that's the norm.s.distribution function. It takes two arguments, our z-value, which was what, negative 2.67, I think. Cumulative is true, right? And that's where we get our p-value. So that is an overview of an example for when we have a population mean, when we know the standard deviation, right, sigma, right, when that's been given to us, right, what do? Right, we state our hypotheses, our null hypothesis. In this case, it's that the company's properly filling them, right? Then we set our alpha value, we calculated our test statistic and our p-value, right? We calculated those, right? That's how we calculate our our test statistic. We compare our test statistic to a critical value, which we learned how to calculate in Excel. And we can use this critical value approach to make a decision, or we can continue and calculate the p-value, the probability, and use that to compare it to our alpha that we've set to determine whether to reject the null or not. Notice that in both approaches, the critical value approach and the p-value approach, we come to the same conclusion, right? In this case, it's that we reject the null. The null says that the company is properly filling the cans. So by rejecting the null, we're saying that this is not the case, and in fact, they're underfilling the cans, so they're in violation. So in the next video, we're going to talk about the 1 and 2 tailed test, because I think this video is getting a little long. So again, I hope that made sense. If not, go back and rewatch this. If it's still not making sense, let me know, and we can do another example together.